I guess. Okay. So we've just talked about electromagnets, and we're seeing that an electromagnet is always made when a wire is wound, when a wire is turned several times on an electromagnet, and later on we shall see that when we have a coil alone, like this one here. Can you see this, guys?
Yeah.
Yes, later on, I'll introduce you to this after looking at some electricity, where we shall be combining electricity and magnetism. We shall find out that when you have a coil like this, and the current is moving through like that, it behaves, that coil there behaves as a magnet. So in other words, from electricity you can get magnets, and from magnets you can get electricity as well. So the two depend on each other. So that is why when you have a magnetic material, for example, iron, and it is placed inside that coil, it is going to form what we call an electromagnet. And this is an example of some of the applications of electromagnets. This diagram here. When the current is on and this part here is placed in contact with the components, or with the source, for example, you have rubbish, it can always pick out all those magnetic materials. Simply take them somewhere, switch off, and then all of them fall off. So that simply tries to tell us that an electromagnet is going to behave as a magnet when current is flowing around it. And once the current stops flowing, then it stops being a magnet. So that is what we all need to know about electromagnets as per now. Later on, like I've said, that we shall be going further with this. And I hope that by now you can answer this question here. Part B, it is saying that a soft iron rod and a steel rod each have coils around them. Both rods are initially unmagnetized, so they are not magnets before. The coils are attached to circuit as shown in the figure. Now the question says that copy the table below referring the soft iron rod and the steel rod in the second diagram. Use the following segments to complete this table below. Magnetized, loses its magnetism, keeps its magnetism. I would like Mega to answer for us this question. Mega, when the switch is closed, what happens to soft iron and then steel? Just choose the answers from these.
When the switch is closed, the soft iron will get warm.
It will be? The answer is either this one, or this one. So which one would you go with? What does it read? How does it read? Are you sure? Then what happens to the steel? What should I put here?
I think that will also be.
I'm sorry, I beg your pardon? It will be?
I think it will be also magnetized.
Okay, you need to be sure of your answers. That is correct. And then when the switch is open, what happens to the soft iron?
It will lose its magnetism.
Okay, loses its magnetism. And then the other one?
Will keep it.
Okay, this one keeps. keeps its magnetism. Okay, that is very good. That is very good. Let's check the next question here. Which ones apply to force between rods when the switches are closed? Choose one. No force, attractive, repulsive. They are here. Dear, what would you say? Which force attracts between the two? What force is here? Is it attraction? Is it repulsion? Is there no force?
I beg your pardon, sir.
The question is here. Can you read it for us? Roman 2.
Which words apply to the force between the rods when the switches are closed? Choose one from no force, attractive force, repulsive force.
Okay, so the rods are here. Which force attracts between them? Is it no force? Is it repulsive? Is it attractive?
I think it is attractive.
Attractive. How do you arrive at that answer? How do you conclude that it is attractive? I mean repulsive. Did you say repulsive, attractive?
Attractive.
Attractive, yes. How do you reach to that answer? Yes, Sunil. What are the poles at A, B, X, and Y? Sunil?
Yes, sir.
What is the polarities at A, B, X, and Y? North, south, north, south. What do you say?
Is A south?
Is A south? I'm also asking you.
Okay. I think A is
A is
south.
why do you say so? Dear, what do you say? Is it south? Is it north?
Yeah, I guess it.
Yes?
I think it's south, yeah. No, north, maybe north.
It is north. Why are you saying that it is north? Patel, for you, what do you say? Yes, Patel, for you, what do you say?
Let me see what I think.
Yes, we need to conclude the force. We know that if the poles are like poles, they repel each other. If they're unlike, they attract each other. Now we've been given a task here to tell. But before you tell that, we must be having the poles first. So we have not yet agreed. Some people are saying south, some people are saying north. We need to conclude A.
I say, sir, I say where there is the positive part of the battery, that is the southern part. And where there is the negative part of the battery, which is the small one, it is the north.
So you're also agreeing with this?
So A is plus, so it is south.
Okay, the first thing that I'm going to do here is this, that first of all, look at your arrows. This is the current flows like this. Since this one is on top of the soft iron, so the arrow will be like this. So behind it will be going down, in the front will be going like this. And then behind it will be going down like this. So look at where the arrows are pointing. Stretch your hand. Make the fingers point upwards because the arrows are going upwards. Where is the thumb? Is it the left? Is it the right?
It is right.
It is the
on
right.
my
So,
side.
so which means therefore that this one becomes the north. Remember the right hand grip rule. You hold the material with your right hand, but make sure that the fingers are pointing in the same direction as the current. And where the thumb is, that is the north. So A is the north, this one becomes the south. So likewise, current flows like this. I hope that Mega we are together. It goes like this, like this, like this, like this, and then down. So meaning that even this one here becomes the north, so it becomes the south. So because of these two here, then you can talk of attraction. I know that dear, you did guess this. Did you guess?
The attraction I guessed, but the North Pole I knew that.
But okay, all right. So I hope that you've got the reasoning there. So here our answer is attractive force. Yes, Sunil. Which of the two arrangements in the second diagram would be used as the electromagnet on the crane to lift the metal yard? Which one would be a diagram for an electromagnet? And why? Is it for the soft iron? Is it for the steel? Yes, Neil? Which of the circuit diagrams would be used for an electromagnet? And what reason do you have?
Second one.
Yes?
Second one.
Which one is the second one? The one for steel, the one for soft iron?
One for steel.
The one for?
Steel.
Steel. Members, do we agree with her? As an electromagnet. Mega, do you agree with her? I hope that you wrote down these members.
Also, it is a soft iron.
You changed your mind. I hope that you wrote down this one here that electromagnets are materials which behave as magnets or become magnets only when current is flowing around them, and when current stops flowing, then they cease to be electromagnets. And we say that these ones are soft magnetic materials. Soft magnetic materials. And an example of these ones is soft iron. Soft iron. And that is what we wrote down here, I guess. Yes, that is what we have here. So soft magnetic materials are used to make electromagnets. And an example of this is steel. So don't lose that mark there. So here we are going to use steel. Sorry, we're going to use iron. Patel, the last question is yours.
State one disadvantage that an electromagnetic could have in comparison with a similar sized permanent magnet. One advantage is that an electromagnet is used when it is in need unlike a permanent magnet, which is always having which is always magnetized.
Okay. Okay. The others, what do you have to say?
And when it's an electromagnet, it does what it is given to do, while a permanent magnet always does what it is not supposed to do.
Okay, that is correct, but the best answer is this. Have you seen that?
Yeah.
What does it read?
Produces the strongest magnet.
Very good, and that is the answer. So if the materials are of the same size, that is why in this experiment here, we said, in this experiment here, we said that both iron and steel are of the same dimensions. They have the same length, width, circular, everything is the same. But when the switch is on, they are both going to get magnetized. But what we see is that iron and steel attract the iron filings, but then iron attracts more. And what does this mean? It means that it is going to form a stronger magnet.
Yeah.
So that is the answer that we've got to give to this part here. Number 12, we have 15 minutes. State two advantages that electromagnets have compared with the permanent magnets. Okay, we have seen this. You can add on your other one. This one forms a stronger magnet. The other one it is it can be used when it is required. Okay. Then part B, for each of the lists below, choose the option that should be used to give the strongest electromagnet. Strongest electromagnet. From the video that we watched, what produces the strongest magnet? Actually, here we can just add on this in our notes. In our notes here, electromagnet. Let me just add on something here, and that is factors. Where you stopped factors. Number one, number of turns. Mega, are you there? Mega.
Yes, I'm here.
Okay. Okay, so number one is the factor, the more number of turns, the more the stronger the magnet is. Another one, current. Current flowing. The more the current, the stronger the magnet. And then number three, shape. And for this case, we said that U-shaped are stronger. U-shaped are stronger magnets. And that's why when we go to motors, the magnets are stronger. So those are the factors. Now, connected to that, when we answer this question here, I hope that you can answer it now. You can answer this question. Are you done with this? I hope that we are done with this. So which means therefore that our answer here is going to be equal to this. The more the number of turns, the stronger the magnet. And then the type of core, in other words, the inside part, it should be iron. Iron materials always form the strongest magnet. And then current, the stronger the current or the higher the current, this is the answer here. So that is what we've got to answer on number 12. Patel, I hope that we are together here. You're following closely.
Yeah.
So what I need you to do, you have this book with you. If possible, you can print out this page, end of chapter questions, and then you try them out. Again, if possible, so that you keep this. Or, and actually that is the best thing that you can do because you don't have the hard copy. If you were at school, you would be having this and I'd be marking inside your book. But since you don't have this, print out this page and then you answer the questions there. Now, I wanted to talk about one other thing, and that is about induction method. I know that you read about this one as well, but I wanted to comment about it as well. Let me just use the notepad here. Induction method of making a magnet. And if this is our magnet, if you bring another magnetic material, this is the material to be made a magnet. To be made a magnet. And we realized, and this is what you saw Patel last time, that when you have a magnet, and then you get another small metal, put it in contact with the magnet, after some time, it also becomes a magnet. That is what you saw last time, not so? With your thing concerning the, I think it was the sharpener, which you had placed on the magnet for some time. Do you remember?
Yes, sir.
Yes, so this one, in contact, while in contact, you can also draw this, by the way, because I'm just summarizing. With the magnet, it also becomes a magnet. It also becomes a magnet. This is a permanent magnet. That is a permanent magnet. Now, one other thing that we need to remember about this is that the side closest to the magnet attains an opposite pole. Gets an opposite pole. So Sunil, if this is south, what would be the polarity here?
North.
Very good. It would be the north. Oops. Okay, so it would be the north. Okay, that is great. That is great. So this will be the north. So if this is the north, then this one becomes the south. Now, this is my question. This is my question. Can I go? Okay, let me first leave this. The question is this, that I have this one as my permanent magnet. And then I have two materials. This is the north, this is the south. I have two materials. This is material X, this is material Y. Dear, can you tell me the poles on materials X and Y?
X is north.
Which one, which side? Okay, this is north, this is south. Okay.
Yeah.
Then how about for Y?
Oh, yeah. Oh yeah, Y is also north.
Okay, so this is the north. Okay, now another question which is coming to Mega as we are concluding.
Yeah, north.
Oh, sorry, north-south. So the question which is going to Mega again is that why do these ones repel each other? Why do they spread? away from each other. I've already given you the answer.
Because they are like poles.
I've already given you the answer. This one spread away because like poles repel. Okay, so that is the end of our lesson. It is good that you've interacted, you've tried to remember what you wrote down, and you're able to answer some few questions. Please, I just want to find out from you, what new thing have you learned today that you had not seen before?
Electromagnets.
Oh,
Electromagnet.
okay, that is fine. So that is the end of magnetism. So meaning that when we meet again next time, we shall be beginning with the static electricity. Static electricity. You can read in the course book, or you can do anything. We shall be beginning from there on Monday next time. Today I wasn't able to come to see you because I wasn't feeling well. So moving there I wasn't feeling well anyway. And I hope that you can hear the way I'm speaking. So that is the reason, meaning that I can log off.
Yes, sir, no problem.
I can log off and then I say bye-bye. I hope that you have written my notes. There'll be the first thing, there'll be the first things I'll be checking when I come there.
Yeah.
Okay, sir.
All right, have
Bye-bye.
a great night.
Thank you.
Thank you, sir.